I will begin. Dear Father, we thank you for this day. Thank you for these students. We pray that you'd help us to use this time wisely, Lord, just to glorify you in what we do. In your name I pray, Lord Jesus. Amen. All right, so I have a certain disagreement with the book, which I must settle. So sequences. I cannot stand for the terminology that he uses, so let me just make a little table to try to settle it. So let's see here. Me, book. All right. So I say that if a sub n is less than a sub n plus 1 for each n, then a sub n is, I like to say, strictly increasing. Okay. The book just says increasing. I do not like this terminology. Now, if I have a sub n is less than or equal to a sub n plus 1 for all n, all right, then I say that it's an increasing. All right, the book says it's non-decreasing, which to me is weird. And not just me, most of the rest of the mathematical world agrees with me. And of course, since math is governed by consensus, like all truth, sorry, just trying to be a good Democrat. Let's see here. Oh, I'm sorry. Let's see here. A means scientist. Let's see here. A sub n. If a sub n is greater than a sub n plus 1 for all n in n, then I say that that makes the sequence strictly decreasing. All right. The book says decreasing. I think you see where this is going. The book is consistent, just wrong. And then a sub n greater than or equal to a sub n plus 1 for all n. Then I would say that it's just decreasing, and the book would say it's what? Non-increasing. Very good. Weird. Anyway, just so you're aware, I will use my terminology, not the book's. So I hope you can deal. So, I mean, this terminology does have some perhaps odd side effects. What does it mean if the sequence is both, what if a sequence is both increasing and decreasing in my terminology? And let us understand, I will be using my terminology because I'm me. So, suppose you have a sub n less than or equal to a sub n plus 1, right? And you have a sub n greater than or equal to a sub n plus 1. Let's see here. This would be increasing, right? This would be decreasing, right? If you have both at once, what does it say? It's constant, right? This would imply that a sub n is equal to a sub n plus 1, right? For all n. If this is true for all n, then this is true for all n, right? Which says that it's a constant sequence, right? All right, so constant sequences are both increasing and decreasing. All right, let's see here. Example the book gives, I'll look at for a second. Suppose you have a sub n is equal to n over n plus 1. Right? Now this one I think we could just do by inequalities. All right? So let's try to decide if this is increasing or decreasing. I mean, honestly, the first thing I would do And this isn't a proof, but note the range of the sequence is what? It's 1 over 1/2, right? And then you got 2, what? 2 over 3? N equals 2 gives you, n equals 3 gives you 3 over 4, yeah? And so forth, right? So it looks like we ought to be able to show that this is an increasing sequence, right? All right, so I know you guys are rusty on inequality arguments, so let's just kind of like work at it. I suggest we start with an plus 1. What's an plus 1? Oh, you know what's a better, excuse me, I'm just remembering now. Forgive me. Certain things just rush back into your mind all of a sudden, and this is one. This is kind of a pain to think about, right? What's an easier way to think? How about this? If we have a sub n plus 1 over a sub n, it should be what? Assuming that we're looking at a non-zero sequence, we can do this, right? It should be what? Less than or? I think that has to be greater than or equal to 1, right? So that criteria is the increasing criteria, right? If we can show the ratio of the n plus 1th to the nth is, or if you don't like that, you could do what? You could do a sub n divided by an plus 1 is what? Less than or equal to 1. You got choices. So which one do you guys want to attack? Let's look at this one, right? So we have a sub n. Let's look at a sub n plus 1 over a sub n. What's that equal to? N plus 1 over n plus 2, right? Divided by n over n plus 1. What's that, though? Looks like to me that's n plus 1 squared divided by n times n plus 2, right? Agree, disagree? Let's see here. I'm trying to show that that is larger than 1. So the game I play here is I want to make this, well, first of all, I'll write this out a little bit. This is n squared plus 2n plus 1 over n squared plus 2n. I'm not sure that that's helpful or not. I want to show that this is greater than or equal to 1, right? So I'm allowed to manipulate, what do you do with fractions, right? You can either what? If you want to let a over b to be greater than c over d, what are the two things you can do? You can either make c smaller, right? Or you can do what? Yeah, make d bigger. Assuming we're working with positive stuff here, right? As we are. So what do you think I should do? I think I should make c smaller. Is it clear to you? It's clear to me that this is greater than or equal to n squared plus 2n over n squared plus 2n, right? Because what did I do? I decreased the numerator by 1. But this is equal to what? It's equal to 1. So there you go. This is a proof. This proves, right? Thus, a sub n equals to n over n plus 1 is an increasing sequence, right? My initial numerical evidence up here, right? This up here, this is not a proof, but it's plausible. This basically gives me a plausibility argument, right? So that's not proof, but let's say it's plausibility. So we can oftentimes argue for something being plausible just by giving numerical evidence, but proof has to be given in terms of specific mathematical step-by-step stuff. All right. So Can you guys tell me what's a greatest lower bound and a least upper bound on this thing? On the range? Looks to me like the minimum of a sub n is 1/2, right? And it looks to me like the least upper bound, or as I prefer to say, the supremum, is 1, right? I haven't proved that. This is a conjecture, of course, and I really don't want to prove it for you guys, honestly. That's not really what this course is. The proof of that would be a pain. The book has a great picture to kind of convince you, to give you a plausibility argument that the supremum, or the least upper bound, is 1, right? And, well, anyway, I'll shut up. So if, comment, I would point out something, right? If a sub n is decreasing, if a sub n is increasing, what does that tell us? Just think about it, right? A1, A1, A2, A2, A3, A3. What's the story go here? Decreasing means what? This is right. On the other hand, this one. So if you think about this, this suggests that A1 is going to be the max, right? And over here, A1 is going to be the min of the range. Some kind of common sense, but yeah.
Would those be two different sequences?
Yeah.
Oh, okay,
yeah,
okay,
I mean,
okay.
yeah, unless it's a constant sequence, in which case the max is the min is everything that it ever takes. It's all kind of boring, but all right. Okay. Let me show you another example. And here we're going to introduce a new thing. I'll do this just as an example, actually. So this is called the factorial, n factorial. What is n factorial? N factorial is n times n minus 1 times n minus 2 times 3 times 2 times 1. But that's kind of a schematic formula, let's say. A more careful definition is 0 factorial is by definition 1. 1 factorial is by definition 1. And then n factorial is defined recursively to be n times n minus 1 factorial for n greater than or equal to 2. So this right here, folks, is the definition of the factorial. Okay? So like, we can easily show that the factorial is increasing, right? Like an plus 1 is what? Suppose that an plus 1 is n plus 1 factorial. Well, by definition, that's n plus 1 times n factorial, right? Which is quite clearly greater than or equal to n factorial, if n is greater than or equal to 1. And what's that? Well, this is a sub n, right? So I can just show directly here that a sub n plus 1 is larger than a sub n, right? In fact, it's strictly increasing, isn't it? So if you look at this sequence, right? What's it going to look like? It's 1, and I'm starting from 0, sorry, n equals 0 to infinity. Sometimes we start sequences at 0. I try to state all the theory in here just starting at 1, but the truth of the matter is sometimes we have examples where we like to start at 0. I guess if you're a glutton for punishment, I would state all of the theory here in terms of like an arbitrary lower bound. But it just adds an extra level of clutter to everything, so I don't do it as to be nice to you guys. But at the same time, every once in a while, I have to give you an example that starts at 0, like this one. So 1, 1, 2 factorial is 2 times 1, which is 2. And then 3 factorial, 6. And then 4 factorial, 24, 120, 720, 5040. That's all I know. But by the time you get to 10 factorial, I mean, this is 6 factorial here, right? 5 factorial. Look at that. 7 factorial is already 5,000. Factorial gets really, really big, really, really fast. The reason we define 0 factorial to be 1 and 1 factorial to be 1 has to do with combinatorics, right? Counting. This makes formulas appear in a natural way. So hopefully you'll appreciate that as you take your statistics course and we do some things in here as we go on. Any questions? So another example, if C is greater than 1, then if we look at A sub n equal to C to the n, he says this is a sequence which increases without bound. I'll put it in my terms. It's strictly increasing, okay? Without bound. Without bound means what? It means that the range has no upper bound, all right? Okay, so like, if we look at A sub n plus 1 over A sub n, what's that equal to? But by laws of exponents, this is what? C, which is what? Greater than 1. So therefore, you know, A sub n plus 1 is greater than A sub n. Which is to say that it's an increasing sequence, right? Now, if you find a bound for it, you can easily, if you could imagine finding a bound, you could easily find a contradiction, because if you just keep multiplying by C a few more times, you'll get past it, right? Here, let me show you. Suppose that Cn was less than m for some m. Suppose it did have a bound, all right? Let's see here. What could you find a contradiction? Could you prove that that's crazy? You can't? Let's see here. I can't think of it right now either. I'm sorry, guys. Sometimes my brain doesn't work. What's that? What's that? Oh, it requires the Archimedean principle. Is that what's up? Is that what I'm up against? Why are you saying Archimedean principle?
Just that you can
Find some larger n, such that what? I mean that sounds hopeful. See, there's going to be a YouTube comment from this. This is not good. Nerds are going to come upon us and show me what's what. I will be out nerded. I accept it though. Let's go on. Let's see here. Well, anyway, I'm gonna leave that as an open question for now. I'll try to come back to it in another class. Okay, guys? I'm quite certain, though, if you assume that there did exist such an n, all right, then you could prove something absurd, all right? Yeah, take the log. Yeah. Oh man, I was trying to see. I should have stopped talking about it. Now, how do I know that I can do this, guys? you notice that f of x equals to the natural log of x has df dx equal to 1 over x, right? Which is greater than 0 for x greater than 0. So therefore, f of x equal to log x is strictly increasing function. What does a strictly increasing function do? Strictly increasing functions preserve inequalities. A less than b implies f of a less than f of b. That's what strictly increasing functions do. This is actually a very important idea. And so their idea was to take the log of this inequality. I think that's hopeful. This gives me n times the log of c is less than the log of m, right? Which gives me that the natural log of c is less than the natural log of m over n for all n, which is absurd. Because the log of c is a particular value, right? And as n goes to infinity, what happens to log of m over n? It goes to 0, right? As n gets really, really big, this top number here gets very, very small. But log of c is fixed at whatever it is. C is given, right? So this cannot be. This cannot stand. So it's impossible to find a bound by contradiction. So contradiction is a method of proof, right? If you're trying to prove something, one way you can prove it is to suppose it's not true, all right? In this case, to suppose that there is a bound. And then if you can prove that that assumption creates insanity, it must be that your assumption was wrong, and consequently, what you're trying to prove is true. This is proof by contradiction in a nutshell. Okay. So limits. Now, this idea I just used here, I used calculus to say something about inequalities. The next example in the section, he uses calculus directly to show a sequence is increasing, right? I should probably cover that example. Sorry. I get flustered with my contradiction thing. So here a of sub n equals something like, I don't know, n e to the n, e to the minus n. There. So this thing, we're kind of torn between worlds, right? Because on the one hand, n is getting bigger and bigger and bigger, right? On the other hand, e to the minus n is getting smaller and smaller and smaller, right? So which one wins? Like, so what we can do is we can look at a corresponding function. F of x equals to x times e to the minus x, right? You notice that, like, f of n is equal to a sub n for n equals to 1, 2, 3, and so forth, right? So this function, in some sense, shares the same fate as that sequence. Now, the advantage of the function of the sequence, of course, is that we know calculus for the function, right? So we can bring to bear all the tools from calculus 1 on the function. Like df dx is what? Product rule, chain rule, right? And factor out e to the minus x. What do you got? Right? Now, the exponential is positive, right? So I can draw a number line here. I can put, here's 1, basically. Here's df dx, right? This only changes sign at the critical number of 1, and at 0, it's positive. And then past 1, it's negative. So this function, basically f is decreasing for x greater than or equal to 1, right? So what's this tell me? That tells me that a sub n is decreasing. Right? Of course, just to check my work, check it out. So a sub n equals 1 to infinity, how's it go? First thing is 1 over e, right? What's the second thing in this sequence? 2e to the minus 2, which is otherwise known as 2 over e squared. Then you got 3 over e cubed, and so forth and so on, right? You can easily see that the exponential term is beating that linear term upstairs quite badly too, right? Like e cubed is like 27 or something ish, 25. So, right. Now, if I tried to do inequalities with n and e to the minus n directly, I don't know, it's kind of cumbersome, right? So calculus is helpful in deciding inequalities, right? Because we can use increasing and decreasing theorems from before, so it's an important idea. Okay, I think I made my point. I guess I'm supposed to also talk to you a little bit about the algebra of sequences. I'll be brief. New sequences from old, right? If you're given a sequence a sub n and b sub n, you can define either a sub n plus or minus b sub n, right? Or you can also look at the product of two sequences, like a sub n, b sub n. Or you can also look at what? Like a sub n over b sub n, provided what? B sub n not 0 for all n, right? So the big ones. You can look at the sum product. You can even take a sequence and multiply it by a number, right? Like c times a sub n is what? If I write it in the range notation, that's like c times a1, c times a2, and so forth and so on, right? So once you have a couple sequences, you can easily form new sequences from adding or subtracting them, or even term-wise multiplying them. These are all things we can do. Okay. Finally. Oh my goodness gracious, guys. Limits. Okay, so let me draw a picture to try to get you the idea before I give you the formal definition. So the graph of a sequence is kind of tricky, right? Because a sequence looks like what? Okay, I mean, so let's see, let me try to. So it's kind of hard to plot a sequence, right? So I mean, so what do you guys think here? What would the limit of this sequence be? Supposing that this is 1. So here I'm plotting a sub n versus n, right? So what we'd like to say is that the limit as n goes to infinity of a sub n, in this case, is equal to 1. So let me try to illustrate the idea for you. Let me actually say that this is an L instead of a 1. It's more exciting if I put an L, right? So L defines some horizontal line, basically, right? And if the limit exists, what that means is you can look at some epsilon band. So let me draw a specific one here. Here's L plus epsilon, and here L minus epsilon. All right. And so if you look at this epsilon band, there comes some point in the sequence, all right, such that beyond that point, everything in the sequence fits into the epsilon band. This is what it means for the limit to exist. But it's not that you can do it for one epsilon. You can do it for any epsilon. For any positive epsilon band you pick, if you go far enough out in the sequence, it's trapped in there. So for the one I've drawn right here, I could choose the so-called n to be 4. Right? So I have for n greater than or equal to n equal to 4, we have the absolute value of a sub n minus L is less than epsilon. What's the absolute value? The absolute value of a sub n minus L is what? This is equal to the distance from L to a sub n. If you take the absolute value of the difference of two real numbers, it's the distance between the real numbers. Right? So geometrically what that's saying is, for n beyond 4, everything in here, every last one of them is stuck in that band. Okay? It doesn't matter that there's some misbehaving ones early on, like a sub 1 or a sub 2 or a sub 3. We don't care about those. The limit of the sequence is purely concerned with what happens as n goes to infinity. This is the idea. All right, let me state the definition carefully. If a sub n is a sequence in the reals, and for each epsilon greater than 0, there exists n in the natural numbers such that n greater than or equal to big N implies that the absolute value of a sub n minus L is less than epsilon, then for some L in the reals, all right, if all of that, then we say a sub n goes to L as n goes to infinity, or the limit as n goes to infinity of a sub n is equal to L. If a sequence has a limit, all right, then it's said to be a convergent sequence. Right? If it's not, if no such limit exists, then it's a divergent sequence. Okay? Another definition I should make before I get too carried away here. If we say the limit as n goes to infinity of a sub n is equal to infinity, if for each m greater than 0, there exists n in the natural numbers such that n greater than or equal to big N implies that a sub n is greater than m. In other words, a sequence diverges to infinity, all right, What that means is no matter how big a value you give me, right, I can find a point in the sequence where beyond that point in the sequence, everything in the sequence is larger than that number you gave me, whatever it is. This is not a convergent sequence. This sequence diverges. So a sub n diverges to infinity. Right. If you don't mind, what would we mean if we say the limit is minus infinity? What would that mean? How would I change this statement? If you don't mind, I'm going to do it in color. If this is minus infinity, we say for each n, well, let me say m, let me something else entirely. Pac-Man. Less than 0, there exists n and n such that n greater than n implies that a sub n is less than Pac-Man. Yeah. And I haven't, yeah. I'm saying that this, when I say this, I mean that that holds for each n beyond there, okay? Okay. So just to give you an example, the limit as n goes to infinity of like c to the n is equal to infinity for c greater than 1, right? If you don't mind, I'm not going to prove that. In fact, I'm not going to prove any of the things I'm about to say, but I think you'll believe me then when I tell you they're true. Limit as n goes to infinity of n is, guess what? What is the limit as n goes to infinity of n? It's infinity, right? N squared, infinity. Again, you can study a function which corresponds to the sequence, right? If you have a function like we were talking about over there that matches the sequence at integer points, then if the function goes to infinity as x goes to infinity, then likewise the sequence does, right? So we have a whole bucket of examples from that way of thinking. Are there other ways that sequences can diverge? How about this? Right, in other words, a sub n is equal to minus 1 to the n plus 1. In this case, the limit as n goes to infinity of a sub n does not exist, right? If you want to make the limit be 1, there's always points in the sequence which are minus 1, which are necessarily 2 units away, right? So you can never like squeeze the epsilon band down farther than like plus or minus 1, if you think about it, right? So this limit does not exist. It's not because it goes to infinity. It's something else, right? So these limits also do not exist, but they go to infinity, which is a specific kind of divergence, all right? All right. Enough about what is not. Let's talk about what is. So here's a nice theorem for you. If a sub n goes to L1 and b sub n goes to L2 as n goes to infinity, all right? And if c is a real number, then we have 1. A sub n plus b sub n goes to L1 plus L2, right? 2, if you have c times a sub n, that goes to c times L1. 3, if you have a sub n times b sub n, that goes to L1 times L2. 4, a sub n over b sub n goes to L1 over L2 if L2 is not equal to 0. I suppose to be careful, I should also assume b sub n is not equal to 0 for n equals to 1, 2, dot, dot. What do these look like? These are more fun if we write them in limit notation, right? Like, and of course I can add a minus here too, right? So for example, the limit as n goes to infinity of a sub n plus or minus b sub n is equal to the limit as n goes to infinity of a sub n plus or minus the limit as n goes to infinity of b sub n. Right? Or number 2 in the limit notation looks like this, right? So number 2 says you can pull constants outside limits, right? Although I can only make those steps if what? The fine print at the top matters, right? I need to know that the limits exist in order to make these steps. Let's see here. Would anyone like to see the proof of any of these? All right. Theorem. If a sub n goes to L as n goes to infinity, then the set, the range of the sequence, all right, is bounded. All right. So here's the proof. Suppose the limit as n goes to infinity of a sub n is equal to L. All right. We can let epsilon be equal to 1 and choose n in the natural numbers such that what? The absolute value of a sub n minus L is less than epsilon, where epsilon is equal to 1, right? If the limit exists, I can do this for any choice of epsilon which is positive, but in particular I can do it for 1, right?
What's ST stand for?
Such that. Good question. Such that, yeah. Now, what's this say? This says, this is true, whenever what? I forgot a qualifier here. Whenever n is greater than or equal to big N, all right? Oopsie. So we can unwrap that inequality. What's this mean? This means minus 1 is less than an minus L is less than 1, right? If you have the absolute value of something is less than yada, that means that minus yada is less than stuff is less than yada, okay? One of your basic laws of inequalities, all right? So, check it out. This implies that L minus 1 is less than a sub n is less than L plus 1. Right? That's for n greater than or equal to n. So what can we choose as our bound? To show it's bounded above. Let b equal to the max of a1, a2, dot, 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 a sub n minus 1, comma, L plus 1, right? Then you can easily see that a sub n is less than for all n in the natural numbers, right? And if you let, I need some other letter, let's say gamma, equal to the minimum of a1, a2, an minus 1, and L minus 1, then a sub n is greater than or equal to gamma for all n in natural numbers, right? So in total, we have that gamma is less than or equal to a sub n is less than or equal to big B for n in the natural numbers. And what's that show you? It shows that the sequence is bounded. When we say a sequence is bounded, it means it's bounded above and below. Okay? So there you go. Convergent sequences are bounded. If you find a sequence which is not bounded, it's not convergent. There you go. All right. Well, anyway, we have much more to say about chapter 11, and I'll do more tomorrow. Thanks, guys.